well, I don't know if you have checked what's the talk about, but what I'm going to show is a project that I have been developing for a few months, which is it's a programming language or in a compiler, but it's made specifically for the things that I like, that is sound design and programming microcontrollers. So in this talk that I'm going to give is just like an overview of the project, but you can stop me at any time and ask me questions if you have more details about the things. Okay, so I'm talking about creating a new language, but I want to start with this rhetorical question. So do we really need more programming languages if we already have like plenty of them that are suited for different things, and that each of these languages has different advantages and disadvantages? Some of them are very popular, some of them are said to be very safe and fast. But I mean, even after looking at all these languages, there are still things that if we design it from the scratch to fulfill a purpose, it becomes better. So, and as I mentioned before, the things that I do, or that I like to do in my free time is programming synthesizers and make sound design. And the characteristics of these applications are not like like other applications in which, for example, when you're programming a microcontroller for sound design or digital signal processing, one of the main requirements that you have is that you need a real-time speed. So you need to program it into something that is fast enough in order to react at the moment in which you press. For example, if I press a key and it takes too long the processor to react, what's going to happen is that when you're performing, that delay is too long that it's impossible to play. And it also needs to be like very low footprint your algorithms. So whatever you program, even if it's a very complex thing, you need to fit it into a very small processor with very constrained limitations. And if we take that the same applications, digital signal processing, for example, the design of control systems for robotic applications. If we take all the same algorithms and we put it into computers, the requirements are slightly different, because what we tend to do in computers is to create not only one single controller or one single sound engine, but what we do is like create hundreds of them. If you have seen how a digital workstation where you design audio, you usually drop like, I don't know, 10 synthesizers. So you put like hundreds of audio effects, and all of them need to run very, very efficiently in the computer. And one thing that I felt really annoyed about programming this kind of systems is that if you want to use a nice language, like something more modern, like JavaScript, Python, or something like Rust or Go, all of these languages, you just cannot achieve high performance that is required for these applications. And even if you do, for example, running in a board like this that has a small ARM processor, even if you can run it, the problem is you have the constraint of the real time, what I was mentioning before. It may be able to complete the computation, but it takes too long. So the main option that you have is C and C++, which is quite fast, and usually you have a C compiler or C++ compiler available for all the platforms. So that's good, but one bad thing is that C++ is still very verbose, and the things that you need to do, it can get quite complicated just for doing simple things. So since after work, I usually all these things after work, And since I don't have really much time to delve into programming C++ in order to do simple applications like this, I was thinking that I should design a compiler or something that in which I can represent the things in a simpler way and well, just being more efficient when using my time. So the key ideas that I have for this language, which is called Vult, were that I wanted to have something in which I should be able of making algorithms, implementing algorithms with very high performance. So it should be really fast, and it should be also portable, because if you design an algorithm for one platform, maybe you want to reuse it, and if you have to change it for language or using a different framework, and that's just time consuming. So I want to take exactly the same algorithm, the same code, and just deploy it wherever I want. And the last thing, which is more important, is simplicity. But all these three ideas are hard to achieve when you design a language. So if you think on your favorite programming language, you may while you are using it, you may come up with ideas or situations in which you say, like, oh, maybe if I program it in this other language, this thing is simpler, and some things are simpler here. So it's hard to achieve these three things, and the only way of doing it is by imposing constraints. So the first thing is that Vult is not a general purpose language. It cannot be used to program anything, like all the algorithms that you think, but the things that you can do with it, you can do it quite efficiently and in a very simple way. So just I'm going to show you the things that I'm using in order to get in this case, speed. So when you're programming a computer, in a desktop computer, you have a floating point type, in which I guess that most of us we just use it, and we don't think ever that if I add a +1, is it gonna affect my performance? So it just comes natural. But when you're programming small microcontrollers, a floating point operation, it's a very expensive operation if the microprocessor does not have a specific unit. If you have done Arduino programming and you use a float variable, you may find out that your programs run like 10 times slower. It's not possible to achieve that. But one alternative is using fixed point arithmetic, in which you take integers and you say it like, if I have a 1,000 in integers, then that's going to represent 1. So you just decrease the number of bits that you use for integers, and the other bits you use it for representing decimals. So in this way you can do operations like 1.2 times 3.5, but everything represented as integers. So this one thing that I implemented in Vult is that it has fixed point arithmetic. So when if you want to, you can take an algorithm which is numeric, and when you deploy it, everything it's integer operations, and this can give, depending on the algorithm, it can go like 10 times faster, and also like calculating functions, it can go much faster than that. And if that algorithm written in Vult can run in the ARM microcontroller, when you run it in a desktop computer, it's just it's hundreds of times faster. But that comes with a cost, which fixed point arithmetic has limited precision. So you cannot represent all the numbers, and you always need to think about, is my number too big, which it will not fit, or or the order of the operation that I'm performing, is it gonna degrade the precision, and the result that I'm gonna get is just like 0, or because the number is too small? And other thing that I really wanted to achieve, it was a very powerful inlining. In case of that you are not used to the concept, inlining means that when you make a function call, it usually the processor pushes arguments to the stack, jumps to the location in which the code is, executes everything, and restores back. And that also has a performance penalty. And initially in the compilers like C, you can just add the inline keyword. Other compilers do automatic inlining. But when you have to do like these real-time operations, it's better just having the code there. And one thing that you can do is just do manual inlining. Instead of calling a function, you just put the whole code of your function there, and you have that goal. But the problem is that if you are inlining by yourself, your code starts like growing, and it gets more difficult to read. So Vult has this powerful inliner that tries to do that no matter the size of your function, if you say I want it inlined, it's gonna do it without still having your nice source code. So function calls will not have a performance penalty. Yeah. So, and when I started developing this, it was like, should I generate directly machine code? And I think since, as I mentioned before, C++, it's C++ and C, it's available practically in all platforms. It's much better just to generate from Vult this code, which can be like more elaborated, more complex, a little bit unreadable, and I can just take it and compile it in any platform without any restriction. So, as for all the entire platforms, if I select, for example, C++ and JavaScript, you can use this language in any platform that is supported by these other languages. But there is also a problem here that you inherit all the limitations and all of the other language. Maybe some languages have more freedom to write things like JavaScript. Others are more constrained, like C++. So it makes it more a little bit trickier to target all these languages. And last and the most important for me, it was having simplicity in the code. So, as I mentioned before, sometimes while you're writing code, you need to take decisions on, should I make this more readable, or do I want it to be faster? And the idea with Vult was it needs to be as simple as possible. And I also took a lot of ideas from the non-technical, from person with non-technical backgrounds. For example, more dedicated to art, since as I mentioned at the beginning, my target is synthesizers and sound design. So you cannot start telling a person that wants to design a sound like, okay, first you need to know inheritance, and then you need to learn about classes, and then you need to use, I don't know, Visual Studio or something, and after you know all that, now you can do the sound. So, as I mentioned, Vult is not a general purpose language, so there are things that cannot be expressed. For example, I have a fixed memory footprint. There is no memory allocation, but all the things that you do is just is kind of declarative. What you write, it generates the algorithm, and that's the only thing that uses, which is also good because you can know immediately how big is your program and if you can fit it or not into a microcontroller. So that my target was to achieve something that is simple and readable without compromising the performance. It still needs to run very, very fast. So does Vult looks. If you have programming other languages, it's not that different. You have functions, which you declare with the constructor of fun. And I saw that someone posted a comment on the group. And the selection of this keyword is because when me and a friend we started designing it, we just want to have fun. So now we have fun. And if you see here, I have, it's a little bit, the colors are not very good, but you have some function that returns a constant. So you just give something, it returns a constant. Here in which you have a function which adds two numbers, and then in the main function, I'm calling these two constant functions and passing it to the add. So if we have a graphical representation of that code, it's something like this. You have two constant functions here, which are sent to the add, and I get a signal or a variable x. But so far, there was nothing special. You can do that in any language. But where it start getting interesting is this kind of functions, which are functions with context. So usually, when you create a function, all the variables that are used, when the function exits, everything loses the value. But in Vult, you can have functions which have this memory. Like in this case, value is declared as a memory variable. And if you have used C++, there is something like called static, which has that kind of behavior. But the main difference is that in C++, what holds the memory, what gives the memory is the function itself. But in Vult, every time you call a function, it has its own context. Like in this case, I have that function counter that has memory called value, and every time it's called, it just adds 1 to the value and returns the value. And then here I'm calling it twice. And the graphical representation will be something like this. So see, this counter has internally its own value, and this counter has internally its own value. So this is, even if it looks very simple, this is very powerful because when you design, let's say, a filter or a sound engine or something that needs to produce sound, or if you are, let's think, a controller, every time you call it, it has its own context. And if you want to do something similar in C++, you will have to create first a class and then create instances of these things. But here, just call the function and you have it for free. And well, once we have functions with context, and we start creating like more complex systems, we need to have a way of referring to each of these instances that we have created. And Vult is very simple. This is the same example, but I added a new function, which it's a reset. It's gonna after some time, it's gonna reset the function. So, and here I'm calling functions, and if you can see here, each function call has, you can attach a name. So when you call it, you can provide a name, and after that you can refer to the context of the function with that name. But you can also call other functions and attach that name, and that means that these two functions should act on the same context. So it's like a very, very simple and cheap way of making a class. But you don't need to care about it. And the graphical representation is like this. You have a reset function and a counter, but these two functions go together, and this one, it's separate. This is context B and context A. And this is one of the things one of the things that Vult can do very well. If you have a program robotics in Arduinos, one of the key pieces in control theory is it's a PID controller. So what you usually do, well, here I have this small robot which has some wheel in which I can supply power, which is how fast I want the motor to go. And this will give me what's the speed, and it will give me how much energy is using. So if I want my car, like in this case, if I want my car to go at, I don't know, 1 meter per second, you need some controller in which it tracks which is the current speed, and if it's going slower, it needs to keep more energy. If it's going faster, it just needs to decrease the energy which is applied. So then you use this speed measurement. This is your target speed. You subtract those two, and then you get your error. And this error tells you like you are going 0.5 meters per second faster or slower. And then you can put that into a PID controller, which this is the source code of a typical PID controller, which internally has this, it's a function with context. But, well, and once you have this PID controller library, you create that function. Once you have that function, you practically have the power to control a lot of things, because you just need to provide the coefficients. And if you are doing another application, you just import this function and call it again. And like in this case, this car has 4 motors, 2 on each side. But the tricky part here is that these 2 wheels are tied by that band, which means that if you move one of the motors, it's going to move forward, but that is going to pull the other, and both are going to go at the same speed. But what's happening is exactly like in a tandem bike. If you are with another person, both are supposed to be pushing a little bit, but one of the persons may not be pushing, and you are doing all the job. And so in this case, you need a control system to regulate that. So you need to, you know that both wheels are at the same speed, but you want both wheels or both motors to consume the same energy, and based on the energy that they are consuming, you can tell which one is doing more or less job. And this is the control diagram. You have that one is the previous, which is going to control the speed of one of the wheels. And from here, there is a second controller which is going to measure the energy that the motors are consuming. And based on that, you just put another controller that's going to control the power for the second wheel. And if you have been paying attention, this is kind of simple to do with Vult, because you just call that function twice, and you will get this behavior. The application that I mentioned at the beginning, which I like to do, it's audio synthesis. And what's audio synthesis? If you have an MP3 player, you have pre-recorded music there, and so you just press play button, and the data is read and sent to your headphones, and you get the audio, and that's what's called what can be called like sampling. It's so the limitation with your MP3 player is that you cannot change the music unless you change the song that you have there. So you cannot say like this, I don't like the voice of this singer, I'm gonna change it. And on the other side of the spectrum, we have audio synthesis, in which all the sound that you listen to are actually computed and generated in real time. And it's something like this. You have oscillators, which are like small, I see it as small boxes that produce sound. And then you can pass it pass these oscillators to filters, and then you can start like getting creative with these different structures, creating different effects in order to create more complex sounds. And that's one of the, well, if you like electronic music, you may know very well that all the sounds do not come from real instruments. Everything is generated from, it can be from an analog computer, analog synthesizer, or a digital synthesizer. Let's try this. You may have already seen this, but this is, while I was doing Vult, one of the things that I found out is that, okay, I have my prototype compiler, I can generate, I can make algorithms and create things, but every time I want to generate a new sound or experiment, what I need to do is like write the code, then send it to Vult. Vult is gonna generate C code. From the C code, I compile it, and then I transfer it to the board, and then I test it. And if I don't like it, or if I want to change a small detail on the sound, I need to repeat the same process over and over. And while you are doing software development, that is like that's every day. But when you are doing sound design, that process it just gets it doesn't let you to do what you want. That is just, I just want to design sound. I don't want to be calling the compiler. And for that purpose, I made this thing in a hackathon in Berlin, in which I had to learn JavaScript. And the main idea is that you have, I want to connect my synthesizer, I want to program in Vult, and I want to design sound. But I want to experiment. I want to just play with the code. So this, what you're listening to, is this code that I have for a small synthesizer with all the Vult functions, and this is the main function, and this is connected to the. My MIDI keyboard is connected to the computer, and I'm using the web audio API, the web audio MIDI, which allows you to use to generate sounds, and which is, I think, what's more used for sounds in games. But quite recently, they added support for MIDI devices. So what I'm doing here, I have this synthesizer, and then I can start controlling stuff. If there is something that I like, I just take it. Otherwise, I can change my code and immediately test it. I haven't prepared anything. Let's make some experiment and see what happens if I do this. Phased. Oops. Okay, so I have no idea how it's gonna sound, but let's try. And that's the way that in which you design sounds. If you have an analog synthesizer, well, you have like a big rack, and then you start moving cables and having ideas, and you start patching, experimenting. So this is a little bit the same. And once the best thing is that once I have something that I like, I can just generate the C code and put it into an artboard, which is more reliable than a browser for making music. But still, it's a very handy tool for doing this kind of experiments. Well, now I'm gonna talk a little bit about how Vult is made. I don't know if you have ever tried to make a compiler, or you have started. And it's at the beginning it's like something very scary, right? Making a compiler, or it should be something very difficult. And that's what I thought at the beginning. But I think that the key part of making a compiler is actually using the right tools. And I have been using the Occam language for quite a while. And one nice thing that Occam has is that it's very easy to represent patterns. You can represent structures, and you can find patterns and transform patterns. And that's what the compiler is at the end. You just have, you find patterns, and if you say, I want to optimize this, you make a function that recognizes the pattern, transform the pattern, and then you have your result. So Vult has 3 stages, which are very simple. One is a parser, which just takes the text, my text program, and converts it into this representation. Well, I'm gonna describe them. So the parser in Vult is I use when I started like researching how more compiler development techniques. I found this one which is called Prat. It's a Prat parser, which I found very easy to understand and to start coding the parser. So basically, what you do, you have this text, and after parsing it, you have some representation like this, in which it gives you the structure. It tells you like the plus consists into 2 numbers. And once you have it in this representation, everything is so easy. So well, and then once you have everything, all your source code represented as these structures, what you start doing is like trying to find patterns and transform things. For example, you can simplify constants. If you see that you find 1 plus 1 or n plus n, and both are numbers, you just write a function that detects it and replace it. Like in this case, if I define a rule that if I have a plus, which a number, 2 numbers, just transform it into another number, which actually performs the operation. And I mean, I would say that's it. That's what you do. Just more, you start creating more patterns, and in the case of Vult, the transformations are a little bit more complex because you need to pass all the context. And once you have all that your code transformed, you just need to generate it back to any other language, which is exactly the opposite as parsing. You have these representations, and you want to get text out of it. Well, in the case of Vult, I have right now code generation for C++ and for JavaScript.
Do you describe the rules yourself, or this is what parser is?
No, well, yeah, you have to describe, yes. Yes, but for example, if you check a compiler design book, there are like typical transformations, and you get like yeah. And in the case of Vult, I have to add new stuff in order to get the program out that I wanted. So far, what I have is kind of a proof of concept. I have been developing Vult for, well, actively I could say 6 months. And what I want to do, as I mentioned at the beginning, is like having a language which is simple and which is easy for persons with non-technical background to use it and to really explore it. So one of the things that I have in mind is I want to have Arduino integration. I would like to, every time that I program an Arduino, I just want to use Vult because it's handy and I made it. So. And my second idea is that I want to create plugins which I can integrate with professional audio software, and I can just type my code directly there and use it, or even just deploy it. And I'm going to continue developing the web-based that I showed before, because that's like the simplest way that every person can get into it and use it. And of course, I have a lot of language improvements. There's still many things to do. It's not finished, and it can run faster. So I'm trying to do that. So you can check the GitHub. You can clone it, and these are the persons that have helped me with design or just ideas or documentation. And of course, since it's an open source project, if you like it, you are welcome to participate. There are many things to do in an open source project like this. So if you have further questions,
Can you go to the code, the big code notes?
Let me open.
No, from the presentation.
Okay.
I'm just wondering, where is the output? The output has to be a buffer, right? Some sort of a buffer. And it's usually sized based on something application specific. And you don't have sizing, right?
No, there is no, because everything that you program here is for generating a single sample.
A single sample.
Yes, and when you the buffer, as you mentioned, is application dependent. So when I generate the code, I just call this function in another function which fills the buffer.
So if you want to do something in the frequency domain, something that requires buffering,
yeah,
you can't.
No, not yet. It's possible. It's gonna be possible when I implement the arrays and tables. But currently it's single point. There is one nice trick in which if you want to do frequency domain, what you can do is just put in the beginning a frequency transformation, and then you have the FFT, and the information that you pass are the actual samples of frequencies. So you can create a function which is going to receive a number which indicates which frequency it is, and the magnitude and the angle, and you can process it as if you were processing like each single frequency. Yeah, I've done that trick in one of my experiments, and it works really well. Any other question?
What about input? If you want to have input, audio input, again you need a buffer or a single sample. Or what?
Yeah. Well, for example, in the demo, what it does is that I need to open it. Oh no, it's here. Like this case, what I have defined is that the process function is going to receive input. So if I...
So this is by convention.
Yeah.
This process is by convention.
Yes. Yeah. That, for example, this is like the template for this application in which you're going to receive. There is a process function which is called every time you need to perform transformations or process audio. Every time I press a note on the keyboard, this function is called. Every time I release a key, it's called. And when I change my controls, it's going to call this, and this is the initialization. And just for testing, I have this, in which it has a sine wave, which I'm generating externally, and it's passed. So if I want to do something like have like this volume control, in which my process function receives input, and I have a volume parameter, which I multiply by the input, and then I can control with this.
And input is again a single sample.
Yes.
By the way, your code with the nodes, it sounds noisy, is it?
Sorry?
It's noisy, right? It's not super clean. When you demonstrated the nodes.
Well, that's kind of intentional.
That's actually why I asked about the buffers, because it sounds like a buffer is not, there is a little glitch every n samples or something. Okay, that sounds clean, but okay,
yeah,
that sounds clean,
okay. You can all, since I have seen that the browser has glitches. It's not for example, there. Well, I can also, and this is another synthesizer that I have written here. And this one runs directly in the port. Oh, let me mute this one. And this one is even more noisy. I think I'm having problems with this one. It's not reacting, not doing exactly what I want. But this one is much more reliable. It's incredible how robust it is.
So you mentioned in one of the applications would be to change a voice, and this is what I'm interested in, like auto-tune, things like this. Have you? Well, most of it is frequency domain, right? So you can do this very well.
Yeah. Well, when I mentioned voice, it was more in the sense that each synthesizer is called like a voice. If you can play the two notes at the same time, you can say that you have two voices. But it's also it's gonna be possible as well doing any kind of audio effect. That's the target. In auto-tune, it's an algorithm as well, which you need to have a frequency detection, pitch detection, and just frequency shifting, which it's gonna.
Time domain frequency shifting, but I'm not sure it can be implemented here because you need to overlap some windows, samples. I'm not sure.
Yeah, but I mean, usually you do it sample by sample. You never do. But what you do is you start filling buffers. Let's say that you want to make a delay or an echo effect.
Yes, but it's harder to figure out how to represent it in terms of single samples. I don't know.
Yeah, well, no, actually, it's exactly the same. And yeah, I mean, you can process all the samples.
At least you need arrays, right?
Yes.
Because you need a sample. I mean, you need a window. I don't know, 64.
Yeah, for example, if I want to do a flanger effect, delay effect, and all these effects need buffers. So you need, every time you receive a sample, you write it, you put it into the buffer, and you will read it later.
Right.
And that's
with echo, it's easy, and there are many algorithms that you need a big buffer.
Yeah, but that's one of the current limitations, and I'm gonna have arrays very, very soon. Maybe after vacation.
And what about the? So the target is this small chip here. Is it what is it?
It's a Teensy board. It has it's an ARM without a floating point. It runs 96 or 98 megahertz, I think.
Does it have SIMD inside?
No. It doesn't even have floating point.
Yeah.
But yeah.
Because SIMD is again another challenge, right?
I've been looking at it, and I think that it's the important thing there is once I have my algorithm, I need to reclassify the operations in order to pack it into groups of, I think it's four operations at a time. And yeah, but I have it also in mind, and it's gonna be somewhere possible depending on the algorithm, of course.
And do you have a PC target as a target?
Yes.
Yes.
Yeah, I mean, I can just generate C code, and I may be able to show it.
But you need to have the surrounding I/O somehow.
Let's open this thing. This may sound very ugly, but let's try it. Oh. Yeah, it's weird. Yeah, let me just put the same screen, because I don't know why it's not showing on in the second screen. I'm gonna mirror them. So what I have here is the Digitalize software that I use for music. And this is one of the synthesizers that I was testing for Vult as well. Oh, sorry, this one.
So it's lagging for.
Yes. So, yeah, since I have C code, I can just put it into any target. Yeah, this is just a test that I was making. Yeah, but this is a very simple example, so it's completely possible. And yeah, my girlfriend complains a little bit when I'm doing experiments. You have any other question? I don't know if you. No, thank you for the invitation.